Today we're going to talk about a new theorem. Now so far we've talked about the intermediate value theorem, the extreme value theorem, and today we see our third value theorem, and it is called the mean value theorem. Now again, this is like the other two in that it's an existence theorem. It just is guaranteed that some value exists. What value exists? I'm so glad you asked, because what we notice here is we have a curve, the function AB. See that, how it kind of went over it? Okay, so I have a curve AB. And on this curve, well, connecting the points AB, we have a secant line. So you can see my secant line AB. Well, the mean value theorem guarantees that there will be a tangent line that has the same slope as the secant line. And so here we have a representation of a tangent line that has the same slope as the secant line. And that's basically what the mean value theorem says. Okay, now, in order to use the mean value theorem, though, we have two conditions. And these two conditions are, first of all, the function must be continuous on the closed interval a to b. Closed interval a to b. Okay, it must be continuous. Now also, the function must be differentiable on the open interval a to b. Okay, so the function has to be continuous and differentiable. Now this is the first time we're seeing where both items have to be in order to use the theorem. And here's the algebraic representation of this theorem. The derivative at some point c is equal to the slope of a secant line from B to A. So the instantaneous rate of change must be equal to the average rate of change. Now I'm going to show you a couple others. These just say the same thing, just phrased a little differently. So you can see this phrasing is the slope of the tangent to f at x equals c. So here we have the slope of the tangent to f at x equals c is equal to the slope of the secant line. Same idea, phrased a little different. There is a place where the instantaneous rate of change is equal to the average rate of change. All very important. Okay, well, we're going to look at an example. So here we are given the function x squared, and we have to show that the function, first of all, satisfies the hypothesis. So in other words, we have to say that's continuous. So at f of 0, is there a value? Yes, it's 0. At f of 2, is there a value? Yes, it is 4. And we can see that the limit, as I approach on this function, is equivalent from the left to right. In other words, there's no gaps, there's no jumps. So our function right here, this function here, is continuous on that interval. Okay, now is it also differentiable? Well, we know the derivative of this function is 2. And 2 is continuous. There is no break there. So we have met the conditions. Now we have to find a solution C to the equation f of b minus f of a all over b minus a. So I want to know, is there a point on this graph where the derivative is equal to the average rate of change? Okay, so what is the derivative? Well, we already said the derivative of x squared is, I'm sorry, I made a mistake here. The derivative of x squared is 2x, not 2, which is a line, which is still continuous. Okay, so we know the derivative of the function is 2x. And the average rate of change from 2 to 0. So we're going to have the value of f of 2 minus the value of f of 0 all over 2 minus 0. So we get 2x equals, well, f of 2 is 4, f of 0 is 0 all over 2. So we get 2x equals 2. So therefore, x equals 1. So we are saying that at the value when x equals 1, the derivative is equal to the average rate of change. So if I were to write this out, I would say the tangent line to f of x equals x squared at x equals 1 has a slope of 2 and is parallel to the secant AB. So we just found the value where the derivative equals the average rate of change. Now, a couple of notes on the mean value theorem. Now, the mean value theorem guarantees that there will be a value, but there actually could be more than one value. Mean value theorem just guarantees there will be at least one value. Now, the other note to keep in mind, in general, finding that value that works may be difficult. The theorem only guarantees that exists. So sometimes finding the value is a little tricky, but we do know it exists. But you have to make sure that the hypothesis of the theorem is satisfied before you can apply it. Now here are a couple of examples that we're going to take a look at. Well, we got Calvin Butterball, just in time for Thanksgiving, running a 100-yard dash in 20 seconds. Assume that the function s of t, which gives its position relative to the starting line, is continuous and differentiable. Okay, there we've met the hypothesis. Show that Calvin must have been running at least 5 yards per second at some point during his run. Well, we do know that he has a starting time and an ending time, right? So we're going to assume he starts at 0, 0, but then we're told that he ends at 20 seconds and he has traveled 100 yards, right? Yes. Okay, so those are the facts that we are given. So we are on a closed interval from 0 to 20. Okay, so according to the mean value theorem, we know that there will be a rate of change somewhere such that it's equivalent to the average rate of change, or the slope of the secant line. So 100 minus 0 over 20 minus 0, which 100 over 20 is 5. So then we can guarantee that Kelvin's velocity must have been 5 yards per second at some value of t according to the mean value theorem, because the mean value theorem guarantees that there will be an instantaneous rate of change equivalent to the average rate of change. Let's look at it. Okay, now we are given more of a functional problem, okay? So we have f of x equals x times a quantity x squared minus x minus 2 on the interval -1 to 1. So first of all, we have to talk about it being continuous. Well, we do know f of x, this is a cubic function, and so cubic functions are continuous and also differentiable. So we can say that it is continuous, okay, on the closed interval from -1 to 1, okay? And then the derivative, we know a derivative of a cubic is a parabola, which also is differentiable on the entire time. Okay, now let's go ahead and examine these values. So I want to look at f of 1. What is the value at f of 1? So f of 1 would be 1 times 1 minus 2, which gives me 1 times a -2, which is -2. And then also I need to look at the value at -1. There must be some derivative at a point C such that f of 1 minus f of -1, so I get -2 minus 0 over 1 minus -1. So when I evaluate that, I end up with -1. Okay, so we know that there will be a derivative at some point that is equal to -1. Well, now we need to find that value c. So let us take the derivative then of this function. Okay, so we have x times x squared minus x minus 2. Oh, okay, so when we distribute that, we get x cubed, so f of x is equal to x cubed minus x squared minus 2x, and therefore the derivative then would be 3x squared minus 2x minus 2, and we have to set that equal to -1. Now, some of you I've noticed recently have been making this mistake in that you want to factor, but you forget that you first have to set it equal to 0 in order to apply the zero product property. So I'm going to add 1 to both sides, and I get 3x, and I get that. Now, can I factor this? I think so. It's going to be 3x near the bottom of this page. And then I get what? Minus 1 plus 1. So my values here then are a negative 1/3 and 1. Okay, so those are the two values where the derivative at these values is equal to the average rate of change. So my sentence would be the tangent line to f of x at x equals 1 and x equals negative 1/3 has a slope of negative 1 and is parallel to the chord joining when x is negative 1 and x is 1. Okay.